You know that vectors have to have both a magnitude and a direction, right? Vectors have to have a magnitude and a direction. That is, that's kind of a non-negotiable, and that's what we use most of the time. So what are some examples that we know so far? What are some measurements we know that are vectors? Which is a vector, distance or displacement? One's a vector and one is a scalar. Displacement. Displacement is a vector because it has to have direction, right? Displacement has to have direction. What is a vector and what is a scalar between velocity and speed? Which is the vector? Velocity, because velocity has to have direction. Acceleration is also a vector. Okay, so those are all examples of things we've looked at so far that are considered vectors. Scalars are the quantities that we've learned that only have magnitude. They don't include direction. These are things like distance, speed, time, even temperature, right? I know temperature can have a negative, but it doesn't include direction, right? So those are all examples of scalars.
Weight be considered a scalar?
Weight is a vector. Right? Because weight is how gravity affects mass. So weight is a force. But mass would be considered a scalar. Yeah, there's a difference between weight and mass, and we're going to look at that in our next chapter, but we use those terms incorrectly a lot. Everyone does, right? That's just kind of commonplace that we call that weight. All right, in a previous chapter, we talked a little bit about vector addition. We talked about how to add vectors. Okay, Well, okay, when we say positive, negative, we mean as an indication of direction. So temperature is negative, but it has to do with a numerical value of negative, right? Not a direction value of negative. So yeah, that's a good question. In a previous chapter, we talked about how to start adding vectors. We talked about how do we draw a vector with what shape? How do we draw a vector? Using what'd you say? No. We draw vectors with an arrow, okay? When we add vectors, we can add them in any order, but we draw them with an arrow, and we talked about adding them tail to tip. We talked about having a resultant vector, or is any of that stuff coming back to us? I would like to think so, but it needs to start coming back to us, okay? Vectors can be added in any order. You can add any number of vectors, but we know that the resultant vector is always the sum, right? The resultant vector is the sum total of all of the vectors that we added together. And it always goes from the origin to the tip of the last vector. From the origin to the tip of the last vector. Okay, and so what that means for this example that's given over here, right? Here's the origin. We went 12 newtons north, then 9 newtons. And so my resultant vector is the red one, right? It's showing us our overall sum of our vectors. Let me give you another example and how we saw resultant vector earlier in the class. We looked at something that went east and then they went north, and we said their resultant vector is basically how far they ended up from where they started. Right? We did that process where we solved for the hypotenuse of that triangle. We found the angle. We figured out how far is our object from where it started. That's the resultant vector. So in this case, the blue triangle here is your resultant vector. Okay? When we add vectors, we always add them tail to tip. We talked about this first, right? If one vector goes east, then our second vector goes north. Let me make this a little bit easier for you to see. Sorry. If one vector goes east and then another one goes north, I would not draw them like this, east and then north, because it's not getting me anywhere, right? I need my resultant vector to take me from the origin to the tip of the last vector. So here's the origin to the tip of the last vector. If I draw them here and here, it's not taking me anywhere. I've got to make sure that I add them one right after the other. I don't start back at the origin until I'm ready for my resultant vector. Okay? So when we add vectors, there's two ways we can add them. I'm gonna have us first add them graphically. And so adding them graphically means we actually use a ruler, we actually determine a scale, and we draw them. Okay, we don't ask you to do that a whole lot. I don't ask you to add vectors graphically a whole lot because you can add them mathematically a lot quicker. But I want you to know how to do them. So I need you to all grab a ruler. Right in the middle table right there are rulers. I need every one of you to have a ruler. So on your paper, I want you to add these vectors graphically. And so what that means is that you're going to be very precise. You're going to start with a coordinate system, right? Start with an origin. And I've got 5 different vectors here. 1, 2, 3, 4, and then 5. And I called them D1, D2 for displacement 1, displacement 2, right? Our object here walks 10 meters south, then 30 meters west, then 90 meters south. It does all of this stuff. And so when you draw this, you're going to draw them to scale, right? And you're going to add them one right after the other. When I say to scale, that means you need to determine with your ruler, does 1 centimeter equal 1 meter? Does 1 centimeter equal 10 meters of my vectors? However you want to draw the scale is up to you. But you're going to determine the scale and you're going to draw it out. And then I want you to know your resultant vector. What is the length of your resultant vector? So you need to measure that again. And you're going to report to me what my resultant vector is. So I'm going to give you a few minutes to do this. Algebraically, this is the method we use a lot more often by just adding our vectors using the math, right? Using Pythagorean theorem, all that kind of stuff. So let's say that I walk 10 kilometers east. I'm going to count each of these boxes as 2 kilometers. Okay, so if I go 10 kilometers east, that puts me here. And then 5 kilometers north. Am I going to draw it like this? What's the problem with that? They're not tail to tip, right? They need to be tail to tip. So 5 would put me about there. So my resultant vector goes from what to what? The origin to the tip of the last vector. Okay, so there's my resultant vector. So if I'm trying to find out my resultant, I have to find the hypotenuse as well as the angle because it has to have magnitude and direction. So if I'm going to find the hypotenuse of that, right, this side is 10, this side is 5. How would I go about that? I use what to find what do I use to find the hypotenuse? Thank you, Pythagorean theorem. So 5 squared plus 10 squared, and I get, what do I get? 11.2 kilometers at, right? That's only the first part. That's the magnitude part of my vector. My direction part has to be because I have to tell the person where do I leave, at what angle do I leave, and walk to get to my final place, right? If I want to end up at this location, where can I walk to get there? How can I get there? So I've got to find the angle. And so to find the angle, do you remember how I like to solve for the angle here? Let's review here. What side of the triangle do I have? Let's think about in terms of sine, cosine, and tangent. What do I have? I've got the adjacent side and I've got the opposite side. Okay, I'm going to use tangent. I also know my hypotenuse, but we talked about this before. If I solve my hypotenuse wrong and then I use it to solve for my angle, right now they're both wrong. So if I'm going to do this, I always use second tangent or tangent -1 of my opposite over my adjacent. We use the inverse of tangent when we want to find the angle, right? The angle causes us to use the inverse. So I'll go second tangent of opposite over adjacent, and that gives me 26.6 degrees. And then we need one more thing, right? It's got to have the cardinal directions that go with it. So is it west of south? Is it north of east? Is it east of west? What is it? north of east. North of east. Do you need some help figuring out why that is?
Can't you just say it?
So you can't just say northeast. Okay.
No, the last.
Yeah, you could say it, whatever. If you, okay, here's how I guess I'll explain it. If you go backwards, right? I went north, then east.
So you go back.
No, I went east of north, right? Oh my gosh, I'm saying it. I said it backwards. I went east, then I went north. So to name it, you would go backwards. I'm north of east. The other way, which I like better, is to tell which axes is my angle touching. My angle has to be touching one of the axes. The east axis, the north axis, the south, or the west. So which axis is it touching? East. And so from there, if I'm touching the east axis, I decide, does my triangle swing north of east or south of east? That's the way I like to look at it, right? My triangle swung to the north of east. Okay? Yeah.
What would you do if there was like 3 lines?
Okay, so let's say we went here, then we went here again.
Or like if you went south.
Yeah, okay. So if I went like this,
Yeah.
okay, and I wanted my resultant vector, like that.
Yeah, like how would you say?
Yep. I would still find the sides of my triangle, right? I might make my triangle here and here, and I would find that angle right there.
Yeah.
This would be
No, it's east of south.
east of south. So we can add as many vectors as we want together. What we're looking at here is if this is my resultant, I build a right triangle off my resultant. And so if I'm going to build a right triangle, I might just close it off here and build my right triangle there. And so that's the angle I'm looking at. And to build that, I went south, then east. So I would call it east of south. It doesn't really matter. But again, I'm touching the south axes. So then do I decide, does my triangle swing east of south or does it swing west of south? And it swings east of south. Okay? A person walks 8 kilometers east, then 6 kilometers east. Oh, no, I'm not even asking you to do anything. Okay, sorry, I'd take a step back here. This is vectors that are both going in the same direction, right? Our resultant vector here is 8 kilometers east, then 6 kilometers east. This is simple, right? Because they're both going in the same direction. 8 and 6, so my resultant has to be 14 east, right? That's just a review on resultant vector, but we've already done tougher ones than that. Okay, now we're going to look at what happens if our vector is given to us at an angle, right? Or what happens to us if our vector is given to us not in a pure cardinal direction. We have what's called components of our vector. Okay, we have a vertical and a horizontal component of our vector. And so if you look at a vector here, I would call this Vx and Vy, right? So this one is the x component, it's horizontal, y is the vertical component. So when we're given a vector that's given to us at an angle, we have to break it down into its x and its y components. Because in our equations for kinematics, we can never plug in anything that's got an angle with it. We have to solve things purely in the x direction or purely in the y direction. Okay, let me say that again. We have to solve equations that are purely horizontal or purely vertical. We cannot deal with things at an angle. So if we're given something that's happening at an angle, we have to break it down into its x and its y components. And so it's basically working backward from what we've been doing. We might be given the hypotenuse and the angle, and we have to solve for the sides of that, right? The components that made that resultant vector. Okay? So let's look at what that might say. All right, here's a trig review. Do we feel pretty good about our trig functions? Sine, cosine, and tangent are what opposite and what's adjacent? Okay. All right, when we see theta, that just means the angle we're solving for. So again, if I put this into perspective in a vector, if I have some vector here, this would be the y component and this would be the x component. Okay? All right. That's right. Yeah, if you were using tangent, you would be finding the hypotenuse. But let's try to break down this vector into its components, okay? A helicopter is flying 34 meters per second at 25 degrees south of west. I would go ahead and draw this vector in your example so that we can have some examples laid out. Okay, so go ahead and draw that vector, and then I'll show you what I mean from there. So let me show you, first of all, without the sides drawn on. Okay, I want you to just draw your vector plane. Okay, so let's say I always start with the origin, draw your origin, and it says 34 meters per second at 25 degrees south of west. So I want you to ignore the picture that's given here. Okay, and I'm going to have us just draw it real quick. Okay, I draw my origin, and I know my vector has to go south and west somewhere, right? South of west. And it says my angle is 25 degrees south of west. So my vector, my angle, needs to touch the west axis. And then I complete my right triangle from there. So if you needed to draw the vector on your own, which is going to be something we do a lot, I'm going to draw my vector kind of arbitrarily in that direction, southwest, and then I'll assign more information to it. So the 25 degree angle needs to touch that west axis, right? Because that's what comes last. And then the 34 meters per second would be my hypotenuse. Okay, so the number that's given to you is your hypotenuse, and then you put in your angle. And so now we want to solve for the x and the y components. So what side would this be, x or y? X, right? Because it's horizontal. So this one I might call it Vx, and this one I might call Vy. Okay, so do we feel pretty good about just drawing it and making the labels on it? Right, breaking it into its x and its y components. Now I need to do the math to solve for that. So if I solve for Vx, is Vx the adjacent side or the opposite side to my angle? It's adjacent. So that means I'm looking at adjacent and hypotenuse. So what trig function would I use? Cosine. Yeah, you're right. So it would look like this. Cosine of 25 is equal to Vx over 34. Right? Are we agreeing with that? Because this is adjacent and that's hypotenuse. But let me rewrite this. This is because in order to solve for Vx, what math do I have to do here? Multiply by 34 on both sides. So I'll show you. I'm going to start writing our problems like this. 34 times cosine of 25. Is that a I don't know, is that a notation that you're familiar with? Is writing it that way? Does that feel okay? Okay, we're just taking the hypotenuse times that, and that would give us Vx. So go ahead and plug that into your calculator. 30.81, I would agree, meters per second. Why not? My hypotenuse is 34, so you're right. It would be a red flag if it was coming out bigger than our hypotenuse. So I think we're okay for right now. One other thing I want you to look at with this vector is the x component of this vector going in the positive or the negative direction? It's going to the west, right? So that means it's negative. So we have to include the negative in our final answer there. So that's something that has to be added on. The negative has to be added on there because it's telling us the direction, right? It's not going to come out in our math that that's negative. But since it's going to the west, we have to add a negative on there. Okay? So now if I'm going to solve for my y component, I'm going to take 34 times what? Sine or cosine? Sine, right? Because now my y component is the opposite and my hypotenuse, right? So I would take 34 times sine of 25. And I get 14.4 meters per second. And so what do I have to include with this one as well? A negative because it's going south. Okay, so essentially, these are the vectors we've been working with in order to get 34, right? We just worked backwards this time. We were given the hypotenuse and given the angle. So we do this, we break these down so that now I could go solve a kinematics problem with Vy and Vx, right? I can't solve a kinematics problem if I've got a vector at an angle. I have to break it into its parts. Okay? So let's go ahead and try the next one here on your own. A vector called V represents a displacement of 500 meters at an angle 30 degrees north of east. What are the magnitudes of the vertical and horizontal components? Okay, so you're going to draw the vector first. Oh, is your calculator in radians?
Well, it's just
We're going to start looking at examples now that are actual kind of realistic type motion, right? Where things aren't moving purely horizontal or purely vertical. I'm going to give you kind of a system to use to start adding vectors, okay? To add vectors algebraically rather than adding them graphically, okay? So I want you to maybe, I don't know, do you need to write down the whole problem? I don't know if you guys like to write down the whole problem or not, but here's what I'm going to show you on this problem, okay? It says a mail carrier leaves the post office and drives 22 kilometers in a northerly direction. That just means purely north. Okay, I don't know why we have to get fancy with our wording, but it just means north. She then drives in a direction 60 degrees south of east for 47 kilometers. What is her displacement from the post office? Okay, what's her displacement from the post office? And I'm going to show you why we're going to choose to add them algebraically instead of adding them just with a ruler and a scale. Okay? Does this image give us a good, here's our resultant vector, but does that give us a good, clear right triangle to solve? No, we still have to build a right triangle. But it's going to be hard for us to figure out what those sides are because we've got this one at an angle, we've got that one that's going north. So solving it via our image here isn't going to be helpful for us this time. If you've only got one or two vectors and they are perfectly east, west, south, north, whatever it is, then that's fine. But in examples like this, it's going to be easier for us to just add them algebraically. And so what I'm going to do is we use this kind of simple breakdown. Okay, our job for each of these vector addition problems is to break our vectors into x and y. Every vector gets broken down into an x and a y component. Then we add up all of our x's together. We add all of our y's together and we build a final triangle. We're essentially trying to find the components of that resultant vector that we just drew. Okay, so let's go ahead and just start with this one here, okay? I've got two vectors. The first of which is 22 kilometers north. The second of which is 60 degrees south of east for 47 kilometers. So I've got two vectors that I'm concerned with. And again, if I show you the image, there's my two vectors, right? It doesn't do me a whole lot of good to have it in the diagram, so I'm just going to leave them separate, and I'm going to treat them separately for right now, okay? So what I'm going to do here is we're going to treat each of our vectors as individual. Okay, so my first vector, I'm just going to call V1. You could call it D1 for displacement number 1. It doesn't matter what you name it, but I'm going to call it V1 for vector number 1. And it is 22 kilometers north. I like to go ahead and just draw a simple diagram for that individual vector. That's not a must-have or must-do, but I think it helps. And then I break that vector into Vx and Vy. Now, if I know this vector is 22 kilometers purely north, does it have an x component? No, the x component is 0 because it's moving purely north. And so what does that mean its y component has to be equal to? 22, right? All of the components of that vector are north, and so that's a y component. So that's really simple to break it into x and y, right? The second one now gets a little bit more complex because it's at an angle. 47 kilometers at 60 degrees south of east. And so that's why I think it's important to draw it. So I'm going to go ahead and draw my vector here. 60 degrees south of east, 47 kilometers. Let's review on how we draw our vectors from scratch here. Right? I start with my origin. I draw it arbitrary kind of in the south and the east. And then I figure out it's 60 degrees south of east. So it needs to touch the east axis, and that's where my angle would need to go. The 47 would be my hypotenuse. Does that kind of make sense how that gets drawn? Do we feel pretty good about that? And so what might I call this side right here? I left one thing out of our other one, I'll tell you that. This should be V1x and V1y because they're the x component and the y component of the first vector. So now knowing that, what might you call these sides? V2x and V2y, right? The subscripts may seem overwhelming, but they all give us a piece of information, right? The 2 tells us we're talking about our second vector, and the x tells us when we're dealing with the x component of our second vector. So if I'm going to solve for v2x, would I use sine or cosine? I would use cosine. It would be 47 times cosine of 60, right? Because the x side is adjacent to my angle. So 47 cosine 60, and I get 23.5 kilometers. Is my x component here positive or negative? It's positive, right? Because it's moving to the east. So now if I'm going to do v2y, I'm going to use 47 sine of 60. And I get 40.7 kilometers. Does that need to be positive or negative? It needs to be negative because it's going south. Now this is why it's so important, because our next step is going to be to add up all of those vectors. And it gives us an idea about where our final thing should be. Okay, so step 1 was to break down into x and y. Step 2 is to add all of our x's and add all of our y's. And so I'm going to come over here and say the resultant x component is 23.5 plus 0. So 23.5. The resultant y component, negative 40.7 plus 22. Right? I'm adding all my x's and adding all of my y's. Okay, I've added all my x's and added all of my y's. Okay, and I called them R just because they're the components of my resultant vector. Now, I want to come to this next slide where I have it drawn out, and I want to show you kind of where we're headed here. Okay, those are the components that I just solved for, okay? So let's just take a little step back here and think about our resultant vector we said was going to look something like this. We agree? The blue one there is our resultant vector. And so if I'm going to build a right triangle, my sides are going to look something like that. These are the sides right here that we just solved for. This x is 23.5. The y is negative 18.7. Do our signs at least match up with what we expected? Our y component is negative, and we needed it to be negative, and our x component was positive, which is what we expected it to be. Does that kind of make sense how we figured that out? Right? And so now if our goal is to find the resultant vector, we need to find that hypotenuse, and we can find that angle right there. You could have also built your triangle going this way too, right? It doesn't matter what side. We would have ended up with complementary angles. Okay, so you've got a couple answers that could be correct. All right, now let me tell you one thing. When you plug in Pythagorean theorem, there's no need for you to plug in that negative. Number one, because squaring a negative always gives us a positive. But number two, the negative just told us direction, which way to draw it, right? Which direction to draw it in. So you don't need to plug that in when you do sine, cosine, tangent, or when you do Pythagorean theorem. Don't plug in that negative 18. Just use regular 18. So in my calculator to do Pythagorean theorem, I just go second square root of 18.7 squared plus 23.5 squared, and I get 30.03 kilometers. And then I need to find an angle. Okay, I'm going to choose that angle, right? I always find the angle at the origin. So I'd go second tangent of opposite divided by adjacent. Tell me what questions, sorry, do you know what the direction is? East of south, I would agree. Okay, so how do we feel about that? Right, we've got three main steps, and I want you to maybe write out these steps as well. Step one is to break each vector into x and y. Right? That's step 1. You have to break all of your vectors into x and y. Step 2 is add x's, add y's. Step 3 is build a new triangle. So even on this problem, if I didn't have this diagram, if I didn't have that diagram there, I would have just taken these components. Now I want you to watch this so you know. If I didn't have the diagram, I would have taken the components and just started at the origin and said, my x component's 23.5, my y component's 18.7, and I would have drawn my resultant vector, and it would have been the same there and there. I could have also gotten an angle here if I would have drawn the other way. I could have had an angle that was 38.5 degrees south of east. Would have also been a correct answer because that's the angle that is complementary, supplementary, complementary in a 90 degrees. This one would have been, okay, thank you, complementary. East, no, south of east. That would have been an acceptable answer as well. Okay, so you could have had complementary angles there. You don't need to have both. I'm saying if you would have drawn your triangle like this.
No, but why is it? Oh, so it's for the line D2. It's not for the angle of the X, Y, X coordinate.
I'm not looking at D2.
Oh, why is it not 90?
What? Okay, let me try it again. Did you get this written down so I can erase my sheet? Okay, so I want to walk through this one more time. If I had no diagram, if I did not have any diagram drawn, and I would have come up with VRX to be 23.5 and VRY to be negative 18.7, I would have built a new triangle. So I do that like this. Draw my origin, go 23.5, negative 18.7, and I've got a resultant vector. If I would have solved it just like this, I would have solved for this angle, which would have come out to be 38.5 degrees south of east. That's the same, that's a correct answer in addition to 51.5 degrees east of south. Those two angles get us to the same final location. You can't mix and match them though. We couldn't have had 38.5 degrees east of south. That would have taken us to a different place. 51.5 degrees southeast would have taken us to a different place. So you've got to make sure you've got your angles correct. Okay? That's why they're complementary. So I took 90 minus that, and that's how I know that's that answer. Because here, my opposite side is 18.7, and my adjacent side is 23.5, so you have to pay attention. Now, one more thing I want to bring up before we get to the homework is that in the problems that we did, x was always cosine and y was sine. That is not always the rule. You've got to make sure that you're paying attention to where your angle is and where your sides are. So don't get into a habit of x is always cosine, y is always sine. That's not the case. Okay?